They're not say to stop projects. Okay, section 1.6. Here again, we're going to take the entire week, so 2 class periods on section 1.6. This homework for section 1.6 is going to be due Tuesday next week. Let me double check that for sure. Yeah, due Tuesday. And Tuesday would be February 16. And the outline for section 2.1 is due 2/16 also. So starting next week, we're going to have outlines and homework due on the same day.
So what's, oh, Thursday?
2.1 outline 1.6. Yep. Okay, we are starting, if you're following along in your books, on page 49. There are, this section is proving quantifiers. So remember, the quantifiers are there exists and for all. So we're talking about proofs with for all first. And the proof with for all, the direct, and to let X be an arbitrary value in your universe. The universe and then you're going to do some work. This is going to be like substitution, applying definitions, that type of stuff. And then you're going to come down and show that P of X is true, and then this is your conclusion. So you have to start with let X be an arbitrary object and then state what your universe is. Yeah, natural number, yeah. So let X be whatever it's needed to be and then show that the statement P of X is true. Now, that is the direct proof. The proof by contradiction for that is going to be suppose the negation. Well, what is the negation of for all X, P of X? How do you negate a for all? Yeah, there exists. And not P of X. So there exists an X, not P of X, it's true. So what you're going to do is you're going to assume for all X it's false. This is just a restatement. And what you're going to do is you're going to let T be an object so that P of T is false. You're going to come down and you're going to have a Q and a not Q. Remember, Q doesn't have to be part of the hypothesis. Or conclusion. It could be, but it does not have to be. And then this is our conclude. So those are our steps. Q is just some statement. So you're going to arrive at a statement that you're claiming is both true and false. Therefore, it's a contradiction. Yeah, Q is just some statement. And it might be that pigs fly and pigs don't fly. So let's do some examples of these. Let's look at the direct proof. Prove that for every natural number n, 4n squared minus 6.8n plus 2.88 is greater than 0. So the first thing you do for the proof is you write your proof symbol. This is a direct proof. So the direct proof says that we actually have to, let me go back. Let X be an object in the universe. So what is a universe in this problem that we're looking at? Numbers, So I actually am going to say let n be in the natural numbers. That's our first step. I need to show, this is my P of n statement. I need to show that that is bigger than 0 is true. And I need to show P of n is true. So I have to do something to get around to showing P of n is true. Well, when you first look at that, you have 4n squared minus 6.8n plus 2.88. Okay, let's start with that. By definition, n is greater than or equal to 1.
And then we put it in. Right.
Okay, so I'm going to do some scratch work over here and see how that goes. We don't know what n squared is. Now where do we go?
Can we plug in any number? Can we try to plug in one?
We can try and plug in 1, but that's only showing the proof for 1. We have to show it for all the other infinite number of them.
Well, the book, when they using the book, I didn't really understand. Factor it.
Factor it.
Factor it?
Yeah,
I didn't understand it.
by factoring. So we know, let's see, 4n squared minus 6.8n plus 2.88. What is that equal to?
Four times n minus 10 over 3 times n.
Mm-hmm.
So on your test, are you gonna have an odd number like that?
Mm-mm. No, I do numbers that are very easy on tests. But tell me about this n minus 0.8 and n minus 0.9. Why are they positive? N is greater than or equal to 1, so that tells you n minus 0.8 is greater than or equal to 1 minus 0.8. But what is 1 minus 0.8? 0.2. Yeah, me neither. And n minus 0.9 is greater than or equal to 1 minus 0.9. But what is 1 minus 0.9? 0.1, which is bigger than 0. When you multiply two positive numbers together, what do you get? Yes. Now you can put it all back together. And so for n minus 0.8, n minus 0.9 has to be greater than 0. Thus, if n is in the naturals, then, and this is my restatement, 4n squared minus 6.8n plus 2.88 is greater than 0 as desired. Yeah, note you could not plug in a number. That just shows it's true for that number. You have an infinite number of them still to go, which means it'll still take you all of heaven to do it if you're doing it one number at a time.
But you plugged in
Greater than or equal to. I know n is greater than or equal to 1.
okay.
So I used a lower bound for it.
To show that even at the lower, it's still greater.
It's still greater than 0. The closest to 0 it can get is still a positive value. Are there any other questions on that one? That's our direct proof. So we're going to do another direct proof. Proof symbol. What's the hypothesis for this one? Yeah. I'm going to combine it together with that whole even. So let x be an even integer. Integers. Well, I could have said x element is z such that x is even. You can do it either way. Where are we headed?
We have to combine the units.
Yes. By definition of even.
Like the odds of using
Well, we'll get to knowing more. By the definition of even, there exists a k in the integers such that x is equal to 2k, right? Then what should we do? Substitute. What are we substituting in? For x squared. X squared is equal to 2k squared. 4k squared. Now I need to make it 2 times something. And then we recognize that that's 2r, where r is equal to 2k squared is also an integer. Okay, so we were good to right here, right?
Okay, yeah, you divide two. Okay.
Mm-hmm.
You still have to do.
Well, I'm just trying to get to it so it looks like our definition of even. Even means 2 times the number.
Yeah, that's even. Oh, they just replaced the R.
Yeah.
Okay.
Mm-hmm. Yeah. And where r is, yeah, 2k squared is an integer. Thus, x squared is even. And then do our big conclusion. And so, if x is an even integer, then x squared is an even integer. Not too bad.
Even instead, after we did it 2 times 2k squared, we had just left it as 2k squared instead.
Not 2k squared, but 2 times 2k
Oh,
squared.
yeah, but like they took out the 2k squared since it says 2 times. So it says since 2k squared is an integer.
Yeah. You can do that. I just substituted it in. You don't have to go that far. Any questions on that one? Notice one thing. Do I have one sentence per line? The way I've written it out. So don't hit returns on your proofs unless the English department would tell you to start a new paragraph there. I saw that on a few proofs. Look, I need to hand back papers. Don't leave without me handing back papers. But I saw that on a few proofs coming back. It's always going to be -1 for that. So don't do that. Don't ever start a new paragraph. If you're trying to figure out, okay, how do I get an equation centered? So then you just do \begin center. Type the equation and then \end center. And then just come down here and start typing next line, whatever it is.
So do they think this have to be centered?
Equations, if they're really long, should be centered, but if they're short enough to fit on one line, they don't have to be centered. You can put them in line if you want. And if there's a whole bunch of them in a row, then center them. But make sure that you're doing that. Don't put the 2 lines at the end. Only use that 2 lines for a new line when you really did mean, according to the math department, to start a new paragraph. Okay. Let's carry on. Another direct proof. For all rational numbers x and y, x plus y is a rational number. How do we prove this one? What's the hypothesis? Assume what?
That X and Y,
So I'm going to say let. It's shorter than assume that.
let
X and Y be rational.
be rational.
So Q is rational.
Okay, so we're going to do, there's only one X, but there's two times three. So it's a whole
Um, what you're trying to do, this is all the, this is the universe. And then this is the P of X. Well, this is X and Y. There's two variables in it, P of X, Y. So let X and Y be rational.
Should we not say that X plus Y over two?
That's what we have to prove. There isn't a prove, but there's a comma there. I covered it up. See, there's a comma there. Everything after the comma is what you're trying to get to. Everything before the comma, in this case, is your hypothesis. So we have to show that X plus Y is rational. What is the definition of rational? Let's write that down. Yeah, there exists J and K in the integers such that we'll say R is rational. So R is equal to J over K, where K is not equal to 0. Can't divide by 0. Okay? So that's what we're going. Let's see if I can spell. And so there exists, I'm going to do U and V and S and T in the integers such that X is going to be U over V and V is not equal to 0. And Y is going to be S over T and T is not equal to 0. So this is by the definition. What? It's just a definition of a rational means that I have to be able to make it into a fraction. I can name them whatever I want. I could have named it A over B. And the same thing with the S and T. I'm just naming my numbers something. But I know that they're rational, which means fractions. They have to be fractions. Now, what should we do next?
Well, can we just say that it's true? X plus Y.
Well, we have to prove that it's true. We can't just say anything. And the whole reason for that is because math is almost the oldest discipline around. And people were making a whole bunch of claims, and in the mid-1800s, we were having contradictory claims being made by people. And so they set about to figure out what was wrong and what was right, and get rid of all the incorrect things that were floating around. Hence the advent of proofs. So we don't ever say, well, it seems obvious, so we'll just say it is. Prove it all. Because someplace in there might be something that didn't quite work. So we have to verify everything.
Can we say that? Yeah, that's
Yeah, by substitution. But what are we going to substitute into? Yeah. So we're going to have X plus Y over 2. But what is X equal to? U over V. And Y is S over T. And then we have fractions. What is our gut response to fractions? Atom. Common denominator, right? So I'm going to have UT plus VS over VT all divided by 2. What can we do with that 2? Multiply by 1/2. So that becomes a UT plus VS over 2 VT. Yes.
or by law of rational numbers.
Well, we already knew v was not equal to 0 and t was not equal to 0. So tell me about this. ut plus vs has to be in the integers. And so my x plus y over 2 is a fraction of something in the integers over something in the integers. So this has to be a rational number, right? It's a fraction. That makes it a rational number. Yeah, that's rational. Thus, if x and y are in the rationals, then x plus y over 2 is in the rationals. And we are done. That is the hardest part. But I can't give you a general follow these steps. Pretty much apply any definitions you know. When you have simplified your hypothesis as much as possible, go simplify your conclusion. And hopefully you meet in the middle someplace. That's as much help as I can be. But the more of these you see, the more tricks you learn to do. That's why someplace in that second proof class after this one, things click. And then you feel like you can prove anything. Yeah.
She said that. Yeah, said it was after that.
Yeah, it happens. It eventually will happen. Yeah, I was in my third proof class when it made complete sense to me, but it took that long. So it's very normal. For some people, it's faster. For some people, it's slower. Proof by contradiction. This is the one I actually didn't have you do in the book. I thought about having you guys write this one up, but it was tedious enough, so we'll just run through it right now. What is a hypothesis? It says for all x in the interval 0 to pi over 2, sine x plus cosine x is greater than 1. That's what we're trying to do. Where's the hypothesis on it? So then sine x plus cosine x is going to be less than or equal to 1. Okay? That's a negation of that one. So we're looking at there exists an x, not p of x. So we have an x, and sine x plus cosine x is less than or equal to 1. Now, it's in the interval 0 to pi over 2. So let's look at that interval. What is sine of x in that interval? Positive or negative? How about your unit circle? 0 to pi over 2 is right here. Sine is y. Is the y value positive or negative in that interval? Positive. And cosine values are like the x values in that interval. Is that positive or negative in the first quadrant? Positive. Cosine is also positive in the first quadrant. So, tell me about adding sine x plus cosine x. Positive plus positive is positive, right? Okay, let's combine our two statements. This is going to be statement 1. This is going to be statement 2. By 1 and 2, I have 0 is less than sine x plus cosine x is less than or equal to 1. Now, that can happen. So far, so good. What I'm going to do is look and see about squaring both sides. I'm going to square everything. So 0 squared has to be less than sine x plus cosine x squared is less than or equal to 1 squared by squaring both sides. This note right here, you're not actually going to type up when you type up your proofs. That's just for you to go back and study later and see. So the reader will be able to see that you squared both sides. Now, do some algebra here. What is 0 squared? 0. FOIL that. FOIL our middle. 2 cosine x sine x, right? Cosine squared plus sine squared, 1. They have 1s there. What's your gut reaction? What do you want to do with those 1s? Subtract them. So we subtract them from everything. And you're going to have minus 1 is less than 2 cosine x sine x is less than or equal to 0. Now, that tells you that either sine x has to be less than 0 or cosine x is less than 0. Is that possible in the first quadrant? No. So this is my Q. My not Q is that part right there that I just did. Or maybe you could say that's not Q and then this is Q. So I have Q and not Q. That can't happen. I can't have sine x and cosine x both positive and one of them negative at the same time. So we put a contradiction here. And then we conclude, thus, for all x in the interval 0 to pi over 2, I'll write it right here, sine x plus cosine x has to be bigger than 1. And we are done. Do you see how the Q and the not Q really weren't related to anything at the start of the problem? There's something that you're going to arrive at partway through the proof. That'll be something that's both true and false, not necessarily related to anything you had at the beginning of the problem, which is why they called it Q and not Q instead of trying to relate it to their statement. Oh, to write those lines down, I would put them on their own and then you could reference them. Yeah. If you have 2 separate cases. Any other questions on that? Okay. Then, practice problems. Your guys' turn. So, who wants to do which ones? Are you and Sarah working together again? So, Sarah Lynn and Elise. IE or EI? EI. Then, Preston, why don't you go back and work with those 2 back there, and you guys can do both of these. So this is Joy Gareth, and Preston. And work together. Don't try and do them by yourselves. We're not trying to show off here.